All right, my friends, invisible pen. Section 9.2 is called Parametric Equations. It is way easier than it sounds. For example one is kind of a warm-up type thing, to be honest with you. It is the content of the day, but it's the kind of thing where if I butt out and just let you do it, we're going to find out that you can just figure it out without me. So for part A, let's have you complete the table for the given parametric equations. And so we'd give you one parametric equation for x. So x is equal to t minus 1. And then y has its own parametric equation. Y is equal to 1 over t minus 1. Now, just a quick comment. I haven't given you the table yet, so there's really nothing to do yet. But parametric equations are oftentimes the first thing that we observe about something. So like maybe we're keeping track of something moving on an XY plane, and it's easier maybe to have one person keep track of, as time changes, what happens to your horizontal movement or your X coordinate. And then maybe have a second person in charge of what, as time moves on, what happens to the vertical movement. And so you've got one person paying attention to how your X coordinate changes in relationship to time, and you have a second person paying attention to how your Y coordinate changes with respect to time. So oftentimes it's kind of easier to piece those things out a little bit. So let's just kind of have you play with this. So in this case, your parameter is called t. T is a very common parameter. Theta, in certain contexts, is also very common. So here's a table for you. So we're going to have a column for t values, and then we'll have a column for x values and a column for y values. So let's say I ask you, just to evaluate x and y. For these different t values. Okay, so this would be a super good time for you to pause the video if you haven't already and just see what you can do. And then I'll go through it and make sure that this is what you were thinking. So I'm going to go down and calculate all the x values. So if t is -3, we would just substitute that in and calculate what x is. So -3 minus 1. Now for -2, -2 minus 1, -1 minus 1, 0 minus 1, 1/2 minus 1, 1 minus 1, 1.5 minus 1, 2 minus 1, and 3 minus 1. Okay. Now for the y value based on our parameter value. So if t is -3, we'd end up with 1 over -4, t being -2, etc. There we go. Okay. Now that we're done with that one, let's move on to part B. The directions for part B are for you to graph the function or actually I'll say graph the curve described by the parametric equations in part A. Okay. And so, you know, to graph this, we're looking at just an XY plane. Another name for an XY plane, you will need to know this soon, is a rectangular coordinate system. So if an equation is written in terms of just X and Y, that's considered rectangular form. Okay. Okay, so plotting these points, we would really just pay attention to X and Y coordinates. So -4, -1/4, -3, -1/3, -2, -1/2, -1, -1, -1/2, -2. 0, you have something that's undefined. In this case, you could see if you chose parameters that got closer and closer to 0, then you'd end up with numbers here that get closer and closer to 0 from the negative side, and then numbers here that get closer and closer to negative infinity. So this particular type of undefined is the vertical asymptote kind. And then plotting the positive values. So, so let's see, we're putting in 1.5, we got 1/2, 2, 1, 1, 2, 1/2. Okay. And so, you know, I think a lot of people would just sort of guess that this is what the graph looks like. And so what does this graph look like? This looks like a 1/x graph. And so that leads us to part C. So part C, let's show how to write the corresponding rectangular equation by eliminating the parameter. Okay, so for this, really all you have to do is go back up to the parametric form equations and choose whichever equation looks easier to isolate the parameter. In this case, I like the idea you could always add the 1/, and isolate the parameter. So I'm going to show two ways. One is very standard textbook, and the other one is more advantageous. And a lot of you guys are just about to lose your minds because you see the advantageous way to do this one. But anyway, textbook approach, you isolate the parameter in whichever equation looks easier. I would say in this case, the x equation looks easier. So you could take x equaling t minus 1. You could add 1 to both sides. You'd get that x plus 1 is equal to t. And then you could just substitute that into the other equations. So since y is equal to 1/t minus 1, if you were to substitute x plus 1 in for t, it would say x plus 1 minus 1, also known as y equals 1/x. All right, I just showed that because sometimes you actually need to do those steps. In this case, I think a lot of people could notice like, hey, x is equal to t minus 1, so couldn't you just take t minus 1 out and put x in? The answer is absolutely good for you. You just saved yourself a bunch of time and trouble. So There you go. So basically, honestly, we just kind of taught the lesson here. So there are a couple things you could do with parametric equations. You could leave them in parametric form and then figure out what you need either in a table or you could show it in a graphing relationship. So parts A and B were dedicated to leaving things in parametric form, and sometimes that's the way to go. And then part C shows how to put your parametric equation into a more familiar form by eliminating the parameter. So all some little moves that you could use. All right, my friends. So let's go to example 2. We're almost done with this lesson, actually. Okay, so example 2, I'm just going to ask you to sketch the curve described by the parametric equations. Okay, and then let's give you x is equal to e to the t, and y is equal to e to the 3t. And then I'm going to have the -1. Hopefully you can tell with my handwriting. The -1 is outside of the e to the 3t function. It's not up there in the exponent. Okay? So take your time, figure out what you would do with this. This is a short lesson, so go ahead and maybe pause the video and see what you'll do with it. For me personally, if I was to choose a way to do this of everything that we demonstrated here, for this particular example, I really like the eliminating the parameter option. And then I really like the advantageous approach for that as well. So you could isolate t here and then substitute that expression in and then simplify over here. But even easier, I would say, would be to start with a more complicated piece, use some properties of exponents right here on e to the 3t. Let's point out that that is the same as e to the t cubed. And if that doesn't make sense, just remember if you raise a power to a power, you multiply them, and then you'd get e to the 3t back. Okay? And then that sets you up to use kind of an advantageous substitution where you could take e to the t and substitute x in. There we go. And so we have eliminated the parameter, and now you could graph this on a rectangular plane now that you have it in rectangular form. And just for the record, you absolutely could have done a t-table on it if you wanted. You could have eliminated the parameter by isolating t and then using a bunch of algebra. But for this problem, this is what I like best. So x cubed graph shifted down 1. You could just plug in, 0, 1, and -1 and get pretty far. I'm just going to do these 3 points of accuracy on this problem because I think that we all kind of know how that graph goes. There you go. Okay, one last example, and this example is dedicated to kind of the weird ones that'll come up every once in a while. So example 3, the directions are for you to sketch the curve described by the parametric equations. Okay, so your x coordinate is found by taking 5 and multiplying it by the cosine of theta. In this case, theta is your parameter, and your y value is equal to 2 times the sine of theta. There are a lot of ways to do this correctly. There's t-table, there's eliminate the parameter, all sorts of fun stuff. Good time for you to pause the video and investigate what you would do with it. Whatever you would do would help you to understand what you'll see me do. Sad day, everybody. My blue pen, I think, is running out of ink. All right. Okay, so assuming that you've taken some time to play with this one, I have seen folks be successful with a t-table approach, where for theta, they made a table that looked like this. Whoa. It looked a lot like this, except the lines were straighter. Anyway, you know. And then I think a lot of us, when it comes to plugging things into trig equations, a lot of us are like, you know what angles I like? I like 0, pi over 2. I like pi. I like lots of pi. Anyway, I like 3 pi over 2, and I like 2 pi. And, you know, I've seen a lot of students kind of do this. And a lot of folks will do this, and they're like, you know, if I have to do more, I will, right? That's kind of the attitude there. Anyway, so if you plug 0 in, you'd get, for x, you'd get 5. And if you plug 0 in for theta over here, you'd get 0. Putting pi over 2 in would give you 0 here, and it would give you 2 here. Putting pi in would give you -5 for x and 0 for y. Putting 3 pi over 2 in would give you 0 here, and would give you -2 here. Putting 2 pi in would have you back to 5, 0. And so with these 4 points, it can be a little tough to figure out how to connect those 4 dots. So some folks might add in more angle measures. Maybe you put in pi over 4 or something like that. But another way to get the graph that you might prefer is eliminating the parameter. And you could actually do it by isolating theta, by dividing by 5 and taking the arc cosine and then putting the arc cosine of x over 5 in here, and then doing things we've learned about how to turn a transcendental expression into an algebraic one. You could do that, but I don't think that you will enjoy it. So instead, there's a fun little move, and it's really helpful when you have x and y in parametric form in terms of trig functions. It's where you use a Pythagorean identity for the trig functions that are involved. So what I'm going to do is not isolate theta. I'm going to isolate cosine of theta, and I'm going to isolate sine of theta. So if I isolate cosine of theta, I would find that cosine of theta is equivalent to x over 5. And if I isolate sine of theta, then I would find that sine of theta is equal to y over 2. And then if I was to combine this with the Pythagorean identity that involves cosine theta and sine theta, which says cosine squared theta plus sine squared theta equals the loneliest number, then I could substitute x over 5 in for cosine. And I could substitute y over 2 in for sine. And then I could simplify this, and it would say x squared over 25 plus y squared over 4 equals 1. And at that point, you could look at that and notice that is which of the conic sections that you have studied centered at the origin. So you can see you've got both of these positive, and so this is standard form for an ellipse centered at the origin. And you, just like we already found with the t-table, you from the center could go out 5, and from the center would go up and down 2, and then you could fill it in. So you have a couple of different things you can try here. You can do a t-table approach. That is always there for you. I will say I rarely enjoy that the most, but it is there for you. And then you could also try eliminating the parameter using just basic substitution. And then if trig is involved, you could use an appropriate Pythagorean identity to try to make that a little bit easier. Something that you'll see sometimes is you'll see little arrows on the graphs. If you see those, what it is showing is as your parameter increases, how did this graph come about? And the table actually would be the most helpful. So as theta increased from 0 to pi or 2 to pi, etc., we got these points in order. And so if you ever see these arrows, then that's what that is indicating. All right, my friends, I hope this is helpful to you. And that's all there is to section 9.2. You should have a decent time with the problem set at this point. Take care, everybody.